We are in the era of energy transition. What do you mean by energy transition? Is we are switching over from conventional energy to renewable energy, and that is called energy transition. While doing so, when we are going to meet net zero by 2050 in whole world and India 2070, we need power. The power is produced by renewable energy. And when it is done offshore renewable energy from windmill, you have to evacuate that power. That power can be evacuated only by HVDC and DC cable. There is no other way. Now, while doing so, why this good HVDC compared to HVAC? What is the break-even point? Is more than 400 kilometers or so. Below that, you have terminal cost very high of HVDC. So the AC is preferred. But if you want to carry the bulk power to longer distance, the only answer today in the world is HVDC. This is what beautiful slide summarizes what is HVDC, left hand side, right hand side with all AC terminals, with the DC, what is the power flow, what is the current, what is the voltage. You don't get this kind of slide. This is all right protected. Since I worked on this, you have this. Now I want to show there are too many complicated parameters is moves when you go into this kind of DC designing the HVDC. You can go for this. See now, if I change this, I make the secondary 205 kV, 554 this thing, and you can see the parameters changing. Okay. So this is the beautiful thing, and I have explained how the parameter change from converter transformer, thyristor valve, and then DC HVDC line, bipole, positive, negative. Then you come again inverter, get it back to AC, convert it to this thing, converter transformer, and connect to the grid. So these are the beautiful kind of you say the parameters. In a one slide, you can do changes and observe it while you're doing the studies. Overview. There are two technologies in HVDC. Why I'm telling HVDC? Now you got to get prepared more than AI and ML. And it is hardcore engineering. So there is a potential rise and demand heavily from the world and market that we need HVDC because we're going for clean energy, green energy, renewable energy, and only answer HVDC evacuation DC cable. So if you get into this, your future is bright and all will be paid more than your AI and ML. AI and ML can go for many kind of application, but they are small application compared to all these HVDC. These projects are billions of dollars, and we are already facing the shortage of hardcore engineering. So the viewers or audience should get prepared for this. I can help them out. So if you want more detail about it, I just done it in VJTI, Egypt, Iran, and USA, UK, and all. And also recently, AIT, Asian Institute of Technology. So presentations includes planning of HVDC, overview of voltage source, LCC line commuted current, and then when you require power electronic. Planning of HVDC projects, overview of these things, you will go power electronic for solving AC transmission. Now if you have 50 and 60 hertz, that what I done it in Kuwait, Qatar, and Bahrain and Saudi Arabia. Saudi Arabia is 60 hertz, whereas the grid, Kuwait, Qatar, Bahrain is 50 hertz, you need HVDC block. There is no other answer in the world. Now, power electronic, why we use this? Transmission bottlenecks, steady state stability, transient stability, power oscillations, inadvertent flows, short circuit current, thermal limits with AC. You can overcome all this bulk power transport or long distance 400, 500, 1000, 1500, 2000, 3000 kilometers. But as you expert in AC, AC cannot transmit power more than 400, 500 kilometers because of impedance loading. Now let's see some conventional solutions, series capacitor, switch and capacitor capacitor transfer, transformer tap changer, phase angle. But these are more conventional with limited capability. Now, here we go. When to apply power electronic, apply where power converter matters, dynamic reactive power, conversion from DC for transmission, interface with generating or storage, concern cost, losses, complexity, and reliability. We always look why we want to transfer the power with the cost, with the losses. With the losses in HVDC is high, but it offsets it when you go with more than 400 kilometers or 500 kilometers. Complexity with AC, like reliability, it doesn't exist. You have kind of tripping. This kind of grid stability can be given with HVDC. Now, high voltage direct current transmission, update Edison started first, okay? And most system presently point to point evolving. HVDC, no distance limitation, I told you, control lead flow, high power transfer, fewer lines, narrow row, right of way. Now, important is eco-friendly. Nowadays, the land is becoming very costly, so we got to have smaller land in review. So the HVDC occupies smaller ROW and losses. That's why we go for HVDC. Now, basic bulk power transfer, back-to-back interconnection, fast angle controls, all kind of things. You see the layout of HVDC I have given here: AC substation, AC filters. Then you have converter transformer. The building is valve hall, that is power electronic thyristors, and that thyristor module I have shown you. This will be around 30-35 meters, whichever I have done, and will cost you more than 900-800 million dollars. Now, the distance and the sea land cable transmission power ratings I have given this. Okay, range from 4,000 megawatt to at plus or minus 500, 4,800 megawatt plus or minus 600, and 800 kV we have in Agra, 6,400. So now, how the LCC looks, what are the converters? This. Now you can see these thyristors. Now we don't have mercury, we have powerful thyristor, 6 pulse. It looks like this, okay? HVDC operating configuration in the world. This is monopole, this is bipole, bipole series, multiple terminal. You have a terminal at Agra, and bipole metallic with a metallic return. Moscow people, Russian were asking me, metallic return is better or earth return is better, but it costs the most security is metallic return. Let's move that. This LCC converter operation looks like that. See reactive power characteristic. Now there are many kind of things, shunt, fixed reactors, thyristor fire reactors. When you have with HVDC, you get a smooth of reactive power conversion. Whatever required, it feeds it. But if you go with the switch, you go with the coarse kind of thing, which is damaging the thing. Now, one part of it, reactive power, I have shown you first leg. It is in before the converter transformer in AC substation. Now, harmonic characteristics, somebody was subjected from my side, I given I trained many people for Siemens, and they are there. They are MTech guys. And they ask why the harmonics characters is even or odd at AC side, even at DC side. This is the formula. But to know harmonic filters, I have published couple of IEEE papers taking the live example from ADNOC and Midlist, and I have designed the filters, many things. Recently, I have designed the filters in converter. This is open one, and there are good guys in the world, reactive power, like reactors, trench is the best, capacitor, high volt, you can go with ABB, and the THD, what is required when you do the HVDC design, this total harmonic distortion has to be 1.5, less than. And TIF is a tolerance in telephonic interference, and should be less than 45. If you don't have that, your design is faulty and it will interfere with your telephone industries and it will damage the things, which is not required. Now, this is one circuit with firing angle. Now, this is calculating the impedance of any country looks. Now, what I showed you, single double, and a quadruple. It looks this, and I have blown it up in thyristor module and blown it up in thyristor single module, and then get unit, which is cooled by air or cooled by water. Now, LCC converter station, it looks like this. This is left hand side, you can see AC bus, all you require for reactive power compensation. And this is the converter transformer, very heavy, 300, 500 tons. We have done it in Chandrapur, Padgate. Then we have done it in Middle East. We have done it in Norway. So, and when you do this conversion, when you get into thyristor valve hall, you get into this kind of DC transmission line, require DC smoothing react. Now, HVDC looks like this. AC filters, converter, thyristor valve wall, DC filters. And what is this shown is in this color is indoor. This is the thing. This gives you basic idea how's the layout and all that. Now, modular back-to-back asynchronous, when you require AC 50 hertz and 60, you require this. It is called back-to-back. There is no DC transmission in that, but converted into 50 and 60 hertz. Generator outlet transmission, if you want to control, and all these things I are given. Now, long distance bulk power comparison is given. 3 into 800 kV AC megawatt. Okay, this kind of you require too much ROW, but with the one or two more kind of pole, you can carry that kind of 6,300 megawatt power only with the two tower. You see, it's so eco-friendly. Okay, now if you want to upgrade it existing from here to this upper capacity, the reliability has to increase and synchronous capacity, system capacity has to increase. Now, the economics in this high risk involves with a lot of investment. And the return is also high. You have to calculate that in feasibility. HVDC and fact issue compared with conventional solution. Okay, conventional solutions have power electronics, some limitations, but HVDC and LCC, and now the latest one is voltage source converter. They are the best, and it doesn't have any limitation. Okay, and the flow is very good. Now let us see this. Having been this, now I have given you some presentation. Hope you'll understand. These are the AC line coming in to the switchyard. These are the gantry, and this you enter into AC switchyard with a breaker isolator. Left hand side, you see the shunt capacitors, harmonic filters required because HVDC creates a lot of harmonic. Why? Because you're chopping the current. And this you land again from the gantry to another gantry in front of a converter transformer, which are huge. And then you get into valve hall. In that, power electronics are there, thyristor, then that converted AC into DC. Then you come out with in DC switchyard, and then from this gantry, we take out two lines, plus or minus bipole, that is the DC line, and this is the DC switchyard. Okay, and yeah, this also very economics. Now you see, this circle gives you the cost of wall, filters, transformers, civil work, project. This is done with 30, 40 years of research, and this is a real life example, and we are taken it this kind of percentage you require in economic and everything. Now, Itaipu transmission, Brazil, the highest power producer in the world, visited there, Brazil. That's why those people from Moscow, they were saying, we heard your name in Brazil. But now it is taken over by China. I met recently Chinese great president in Arnhem, Holland, and they are producing 27,500 megawatt in one place. It is called Three Gorges. And to tell you, you will be shocked because of that dam and making the hydropower of 27,000 plus megawatt, it has reduced the rotation of Earth to 0.00 microsecond. That's something mind-boggling. Voltage source. Now, this technology is superior. In voltage source converter, it is also HVDC. It doesn't use thyristor. It uses IGBT. Yeah, IGBT, inverter gas bipolar transistor, which is superior, then you don't require reactive power to compensate. So that much area is saved. It does release and absorb the reactive power. So how it looks? The HVDC looks like that. And the footprint of layout is reduced more than 40%. I'm not going to explain you all details. We do a lot of calculation, but you thumb rule, you take it like that. Simple building and voltage source symmetrical. It looks like this. These are the kind of circuits. Okay. And here you see, I have shown you, these are the IGBT we use in voltage source converter. And now voltage source is associated with offshore windmill. That's why I'm trying to present you this. Now the era, and we're talking more than $1 trillion only for Indian industry or Indian power. And voltage source converter, now you see, so the valve hall is so small compared to LCC, but it's got a limitation up to around 2000, 3000 megawatt. It cannot carry right now 5000, 15,000 megawatt. It doesn't have capacity, but we are doing a lot of research to improve that capacity. The voltage source converter looks like that, and I showed you LCC also.